In the last lecture we saw that some square matrices are invertible and some square matrices are not invertible. But at the moment we've got no criteria aside from the 2 by 2 case for deciding when a given square matrix is invertible or not. And it turns out that coming up with a good criterion is actually very difficult. It takes quite a lot of involved mathematics. So we're going to set off on our journey to finding such a criteria via what might seem a sidestep, which is to start looking at systems of linear equations. Here's the definition of a system of linear equations. A system of m linear equations in n unknowns x1 up to xn, where the coefficients are little a ij and little b1 up to little bm, is just a list of simultaneous equations like this. So, for example, something like 2x1 minus x2 equals 3 and x1 plus x2 equals minus 1 will be an example of a system of two linear equations in two unknowns where the coefficients were 2, minus 2, 1 and 1, and 3 and minus 1 would be the b's. So the connection between those and matrices is that every system of linear equations can be written in an equivalent form using matrices. So saying that this system of linear equations holds is equivalent to saying that there is a matrix equation, AX equals B, where A is the matrix whose coefficients are the coefficients of those linear equations on the left-hand side of the equality signs. X is a matrix, or rather a column vector, whose entries are the variables in the simultaneous linear equations. And B is a column vector whose entries are the things on the right-hand side of our simultaneous equations. Looking at an example, here is a system of linear equations 2x plus 3y plus 4z is 5 and x plus 5z is equal to 0. And the matrix form there would be that this matrix, whose entries are the coefficients on the left-hand side of these equations, so the 2 there comes from this 2, the 3 there comes from this 3, the 0 just here comes from the fact that there's no y term on the second equation, and so on. And then we have our vector x consisting of the three variables x and y and z next, and then finally over here this is the b, which has as its entries the right hand sides of the equations right here. So this is just a simple equivalence arising from the way we defined matrix multiplication. Any system of linear equations can be put into a matrix form like this, and saying that the system of linear equations is true is equivalent to saying that the matrix equation AX equals B is true. So there's a special case where matrix equations are especially easy to solve, and that's when you have a matrix equation of the form AX equals B, like this one, when the matrix A is invertible. So sometimes there may be a square matrix A, and that may be invertible. And the reason that the system of linear equations is easy to solve in that case is because if AX is equal to B and A is invertible, we can multiply this equality on both sides on the left by the inverse of A. When you do that, you get this equation here. A inverse times A times X is equal to A inverse times B. Since matrix multiplication is associative, I could bracket this matrix product here if I liked as A inverse times A times X. But A inverse times A by definition is the identity matrix, and multiplying by the identity doesn't do anything. So what you have on the left there is simply the variables X. What you have on the right is A inverse times B, which will be a certain column vector. So what these manipulations show is that linear system, AX equals B, has the unique solution X equals A inverse times B when A is invertible. To help us study systems of linear equations, it's helpful to introduce a thing called the augmented matrix of a system of linear equations. When you have a system of linear equations whose matrix form is AX equals B, then the augmented matrix is the matrix which you obtain by taking A and attaching B on the right as an extra column. So to return to our example which we saw before, where the matrix A was this 2 by 3 matrix and the matrix B was this, then the augmented matrix, which we write A and then it's usually a line and then B, would be this thing here. You can see that that is the matrix A with the matrix B added as an extra column on the end. So there's the B, and here is the A. On this slide I'm going to give a formal definition of a solution to a matrix equation, because it so happens that we're going to talk about solutions a lot and I need to be precise about what I mean by a solution. A solution of a matrix equation of the form A times X equals B is a vector V, this time of numbers, not variables but numbers, such that A times V is equal to B. So really this is just what you think it is. This is the normal commonplace meaning of a solution of a system of equations. It's a set of variables that a set of values that the variables in that equation can take, which make the equation true. There are various possibilities. A system of linear equations written in matrix form could have no solutions at all, or it could have a unique solution, or it could have infinitely many different solutions. There's some terminology that we use to distinguish between those cases. If a matrix equation has solutions, then it's called a consistent matrix equation, or the corresponding system of linear equations will be called a consistent system. If the system of linear equations, or the matrix equation, has no solutions, then it's called inconsistent.